So we're still in Chapter 6, Exponential and Logarithmic Functions, and Section 6.3 is all about exponential functions. So the first thing we're going to do is evaluate exponential functions. Then we're going to graph exponential functions. Then we're going to define the number e, if you haven't seen before where it comes from. And then we're going to solve some simple exponential equations. So let's start by evaluating exponential functions. So I want to do a memory refresh on all the laws of exponents. So I'm going to do them here on the movie, but then I'm also going to do them again in class because I want to make sure you're very clear on them. If the bases match, the exponents add. If you have one base and two exponents like this, they multiply. If you have two things multiplied together to a power, the power applies to each factor of the product. So if you have a, b, c, d to the power, it's a to the power, b to the power, c to the power, d to the power. So that's called the product rule for exponents. 1 to any positive number, or actually any real number power, is still 1. A is a real positive number, and I have it to the power of negative s. That's the same as 1 over a to the s, so that's the definition of negative exponents. And a to the 0 is 1, where a is any real number. So we're going to use our calculators to do a little practice here, so please bring your calculator and we'll make sure you know how to find all the buttons on it. And this is a little introduction to exponential growth. And chances are you've heard that saying. If you look at the population growth in Placer County over the past 10 years, it's exponential. It's just exploding. So let's define an exponential function. And it's a function that has a particular form, and hopefully you're getting used to the word form now and getting an idea of what it means. It's a structure or a template. It says we have some number capital C times some base A to the power of x. So notice how this is different than the power functions. The power function had x to the 2, or x to the 4, or in general, x to the n. But see how the x is the base in a power function, and the x is the exponent in an exponential function. So a for us is going to be a positive real number. We're not going to look at what happens with a negative base. That's another topic altogether. And so we have a as a positive real number, so it's bigger than 0. It can't equal 1. Capital C can't equal 0, and capital C is a real number. The domain of f is easy. It's the set of all real numbers. The base A is called the growth factor because it controls how fast the function grows. And because f of 0 is c times a to the 0, and we just talked about earlier that any real number to the 0 is 1, so c times 1 is c. C is called the initial value. It's what's happening at the very beginning. What's the population at the beginning? What's the amount of money at the beginning? So let's talk in class about why we need those conditions of a positive, not equal to 1, and why does c need to be not equal to 0. So make sure you're seeing the difference between the power function and the exponential function. Okay, so power function, x is the base. Exponential function, x is the exponent. So everything you've already learned about transformations applies to exponential functions. So remember, we have right and left shifts. So that will happen if you have x plus 3 before you do it to the power. So see how the inside-outside doesn't really work here? You really need the before. So this would be a shift 3 units to the left. The up or down shift is if it happens after the function happens. So the exponential function has happened, and then you add 5. We'll move it 5 units up. A vertical stretch or compress, remember that happens if you multiply after the function. And a horizontal stretch or compress happens if you multiply before doing the function. And remember that multiplying squashes, so this is a compression. So it's backwards from how it seems like it should be. But this is a stretch. Then we have reflection about the x-axis, and that happens if you put a negative in the front. Every y value becomes the opposite of what it used to be. And reflecting about the y-axis happens if you do a negative on the x before you do the exponential function. Okay, so this is just kind of an interesting theorem that's a special thing that happens for exponential functions. So I want to talk about what happens if you take this exponential function f of x that equals capital C times a to the x. And if we then ask, what does f of x plus 1 look like? Well, that's capital C times a to the power of x plus 1. Well, we reviewed property of exponents at the beginning to remind ourselves that we can write this using that property backwards of a to the x plus 1 has to equal a to the x times a to the 1. So now I can see that this is C times a to the x. Well, let's see what happens if I do f of x plus 1 over f of x. So I have C times a to the x over C a to the x. Well, the c's cancel and the a's to the x's cancel. So all that's left is a. Or you can say that f of x plus 1, the value of the function at the next number, is a, the growth factor, times f of x. So this is the proof over here. So notice that this means that f of 5 equals a times f of 4. Does that make sense? So if your exponential function looked like 7 times 3 to the x, then f of x plus 1 over f of x would equal 3. Make sure that makes sense to you. Okay, so then we are going to practice a little bit identifying linear or exponential functions. So exponential functions have that special property where if you do f of 5 over f of 4, it's going to equal a. So that's how we detect exponential functions. So this exercise, we're going to determine whether the given function is linear, exponential, or neither. So think about a linear function. If I have f of x equals ax plus b, so the same thing as mx plus b. So if I do f of x plus 1, that says replace the x with x plus 1. So I'll get ax plus a plus b. We'll rearrange a little bit, and you can see that for a linear function, f of x plus 1 equals f of x plus a. So this is for linear. And then for exponential, we said, oh, f of x plus 1 equals f of x times a. So that's what we're going to use to decide which these functions are. So we're going to say, what's f of 3 divided by f of 2? And in this case, that's negative 7 over negative 4. But then f of 2 over f of 1 is negative 4 over negative 1. So we get 7/4 in this case and 4 in this case. We're not getting the same number over and over again. And in order to be an exponential function, this has to be true, that no matter for what number x, if you do the x one bigger over the one smaller, you have to get a. So we can see that this is not exponential. But let's look at what should happen if I do x plus f of x plus 1 minus f of x for a linear function. I should get a. So let's try f of 3 minus f of 2. And you get negative 7 minus negative 4, or negative 3. And then if I do f of 2 minus f of 1, I get negative 4 minus negative 1. Oh, I'm getting negative 3. F of 1 minus f of 0, I'm getting negative 1 minus 2, or negative 3. So it looks like I have a linear function with a equals negative 3. So it says if it is a linear function, find the function that models the data. So we know the slope, or the a part. So we have so far that f of x equals negative 3x plus b. Well, let's do f of 0 since that's easy. F of 0 would equal b, and we can see from the chart that that's 2. So the linear function is negative 3x plus 2 that describes this data. So you can use the other data you're given as a check. You have a negative 1 here. If you plug in negative 1 for x, and here, it works. So we'll look at the other two in class together. So objective 2 is about graphing exponential functions. So we need to be able to draw their graphs. So it can help to make a little f of x table. And let's do a couple of values. So if I do x is negative 2, I have 2 to the negative 2 power, which is 1 over 2 to the 2, which is 1/4. So when x is negative 2, here is 1/2, here's 1/4. So there's my point on my graph. When x is negative 1, I'll have 2 to the negative 1, or 1/2. So when x is negative 1, I'm at 1/2. Then when x is 0, 2 to the 0 is 1. So here I am at 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. So you can see why I made my graph so tall. And when x is 4, y is 16. So I have this point here. So it keeps going up and up and up. So here's how the graph looks. It explodes in growth. And if you take it back this other way, you can see that it approaches the x-axis as an asymptote, but it can never get there. Because think about this function, f of x equals 2 to the x. Is there any value of x that you can put in there and get 0 for the answer? And hopefully you'll say no. So I'm going to pause here and come back.